Similar, is that right? Alright, you must be familiar with these equations. Let's now talk about another type of pendulum called the physical pendulum. What is a physical pendulum? Now, look at a meter rule I have. If I drill a hole in a meter rule and suspend it, allow it to hang from that hole, this is the equilibrium position of the ruler. If I now pull the ruler to one side, look at this, and leave, the ruler will oscillate about the mean position. This is called a physical pendulum. Alright, let's talk about this. A meter ruler of mass m suspended from a rigid support at A, there you are, is a physical pendulum. Now this is where the ruler is suspended. It is free to oscillate at that point. And this is the center of the ruler, the center of gravity. You know that the center of gravity is the point at which the weight of an object is acting. Alright, the center of gravity of the ruler is G, and the distance of the point of suspension, well, let's go back and look at this again. This is the point of suspension. Let me find a hole in the ruler. And, well, this is my point A, and if the center of gravity is over here, the distance measured from the point of suspension to the center of gravity, we are going to call that by the uppercase D. So what does uppercase D stands for? The uppercase D stands for distance from the point of suspension to the center of gravity of the meter ruler. Point A is at a distance D from the center of gravity of the ruler. If the ruler is now pulled to one side and released, it will oscillate in simple harmonic motion. At any given time, the ruler makes an angle theta with the original position. This is the original position. At any given time, the ruler can be somewhere here, making an angle theta with the original position or the vertical. Alright? Now, this is the distance D. This is the center of gravity of the ruler. Okay? At this position, the weight of the ruler mg acts vertically down. You see, the weight of the ruler will be acting at the center of gravity, will be vertically down. This is the distance D. The weight mg of the ruler is acting vertically down. Alright? This weight produces a torque. I hope you'll remember the concept of torque. You see, when the ruler is displaced, it has a weight mg. And what does that weight do? Weight wants to rotate this ruler. You see, rotation is produced by a torque. So this weight now produces a torque about this axis so that the ruler rotates. So the rotation of the ruler is produced by a torque. And I hope you understand, you remember this. Tau, the Greek letter tau, represents the torque. So the weight produces a torque tau about this pivot position such that tau equal to negative mgd sine theta. Do you understand this equation? Now, if you remember what we did in physics 1, torque of a force about an axis is the force multiplied by the distance. Look at the perpendicular distance. It is this distance. And if this angle is theta, this distance is d, this distance will be d sine theta. Let me draw that for you. Now, this distance is d sine theta. And now, the torque produced by this force about this point will be this force multiplied by that distance. You see, this distance, which is d sine theta, and this torque is a clockwise torque, which is negative. That's why we said tau equal to negative mg d sine theta, and that is the torque produced to make the roller rotate back. Alright, but again, you have to recall a number of results we did in Physics 1. Tau equal to I alpha. In the same way as in linear motion, F equal to ma. In rotation, tau equal to I alpha. So we're going to replace this tau by this I alpha. Here I is the moment of inertia of the ruler about the pivot point, and alpha is the angular acceleration. Is that right? I is the moment of inertia of the ruler about this axis, and alpha is the angular acceleration. Therefore, replacing this tau by I alpha, look at the equation we generated. I alpha equal to negative mg d sine theta. Alright, let's take this equation and talk about it further. Solving for that, let's solve for alpha from here. Alpha stands for the angular acceleration. You see, in the two previous cases, we solved for linear acceleration. But in this case, the acceleration is angular acceleration. Acceleration is negative mgd divided by I times sine theta. Well, I'm going to do a small approximation. When the angular displacement theta is very small, sine theta is actually the same as theta. Have you ever seen that? If the angle is very small, but remember, measured in radians. If the angle is very small, like 0.02 of a radian, sine of 0.02 radian is the same as 0.02. You see? Sine theta is approximately equal to theta when that theta is very small. So I'm going to replace this sine theta by theta, and what will be the angular acceleration equal to? Alpha equal to, alpha stands for what? Angular acceleration is negative mgd over I times theta, where theta is the angular displacement. Alpha is the angular acceleration, theta is the angular displacement. Now, this is the equation for this physical pendulum. Now, can we now compare this with the equation for the simple harmonic motion we developed earlier? Do you remember that equation? This is the third or fourth time I'm asking you, do you remember the equation for acceleration of a simple harmonic motion? I don't think many of you remembers. It is A equal to negative omega squared y. Look at this. Acceleration, displacement. Let's go back to this equation here. Acceleration, displacement. So this equation and this equation are the same. The oscillations of a physical pendulum is a simple harmonic oscillation. The acceleration is proportional to displacement and is directed opposite to it. Just the same as this. Now, can you compare these two equations? Yes. We can now say omega squared equal to mgd divided by I, where m is the mass of the ruler, g of course is acceleration due to gravity, a constant, d is the distance of the point of suspension from the center of gravity, and I is the moment of inertia of this ruler about an axis through the point of suspension. Alright, now you know omega. Omega is 2 pi over t, and omega squared is 4 pi squared over t squared equal to mgd over I. Let's solve for t from here. Solving for t, I get t equal to 2 pi square root I over mgd. And this is the equation for the oscillation of a physical pendulum. Alright, we have now 3 important equations we developed. The general equation for acceleration of a simple harmonic motion, the equation for the period of oscillation of a loaded spring, t equal to 2 pi square root of m over k, the period of oscillation of a simple pendulum, t equal to 2 pi square root of L over g, and now the period of oscillation of a physical pendulum, t equal to 2 pi square root of I over mgd. Alright, we will in the next lesson be using all these to solve problems.